Hi, welcome to week 13 session, Operational Amplifiers. This will be the last session in this course. So the typical operational amplifier has differential input and signal-ended output. The figure shows a block diagram of an op-amp. The input stage is a differential amplifier. As you can see, so the first block or the first stage of the operational amplifier is a differential amplifier, and as you can see we have two input, and the task of this stage is to differentiate between the two inputs, means detect the difference between input 1 and input 2. Okay, then the difference will go to the next stage, and the next stage we have the amplification stage, where this small difference between the two input, if there is a difference between the two input, will be amplified through this stage, and then it will send to the next stage, and the class B push-pull emitter follower will connect the signal to the out of the operational amplifier. So any other device will be connected through this stage. It's like a protection stage for the operational amplifier. And as you can see also, we have two supply input for the operational amplifier, and we have a single output. This block diagram shows the most common stages of any operational amplifier, although there are some exceptions. In some operational amplifier we don't have this class B push-pull emitter follower stage, and in some others there are two output, not one input. But this is the most common operational amplifier block diagram. In this slide we show you the sample of the operational amplifier, and as you can see, this is the circuit sample of the operational amplifier. We have two input, an uninverting input and an inverting input, and as we said before, we have two supply voltage we call plus VCC and minus VEE, okay, and a single output. So this will be the circuit sample of the operational amplifier. The equivalent circuit of the operational amplifier. The equivalent circuit is of the operational amplifier. It's showing as here. So we have two input, and we have an input resistor that is a very high input resistor, and we have a source. This source is the amplification source, so it will be the open loop gain multiplied by the difference between V1 and V2, the difference between the two input. So the difference will be amplified, and then it will go to the output through R out, the output resistor of the operational amplifier, and usually this one is a very small resistance. So we have a very high input resistance and a very low output resistance. Now we'll talk about the ideal op-amp, the perfect op-amp. If you know what's ideal mean, it's the perfect operational amplifier. So the perfect operational amplifier, the input resistor is infinite, so an infinite input resistor, and the current I1 and I2, the current through V1 and V2, I1 and I2 equal 0. So no input current, and as a result of an infinite input resistor. And R out, as we said before, it's extremely small resistance, and the ideal it should be 0 ohm. And the open loop gain, OL for open loop gain is also infinite. So this ideal op-amp should have an infinite gain. And when V1 and V2 are not connected, usually V1 equal V2. Sorry, this one is V2. So that's the ideal operational amplifier. So now let's look at the most popular industrial operational amplifier, which is the 741 op-amp. This one is an industrial standard. It's very, very, very commonly used in many electronic circuit and devices. So the 74 let's see the specification of this 741. So the input impedance of the 741 is 2 mega ohm, and the output resistor, which is extremely high input impedance, 2 mega ohm, is a suitable high input impedance, and R out is 75 ohm, which is a reasonable low output impedance, and the open loop gain is 100,000. That's mean if this operational amplifier is open loop, no feedback, it will amplify any signal 100,000 times. And the input during the bias is 18 nanoampere, and when this operation amplifier is off is 20 nanoampere, which is extremely low current. Okay, and the unity frequency is 1 megahertz. We will see what's the unity frequency in the later slide, and the CMRR is 90 decibel. So these two factors is very important, the unity frequency and the CMRR. In the next slide, we will explain what is this. So CMRR is short for common mode rejection ratio. Common mode rejection ratio. So basically, when the two input of the operational amplifier, if the two input are identical, are the same, the output of the operational amplifier should be 0 because the difference is 0. But this doesn't happen in a real life. There always a variation in the output. So even when the two inputs have the same voltage or have the same signal value, the output might not be 0, and that's because of the common mode rejection ratio. So if an identical signal is applied to both the inverting and the non-inverting input, there should be no change to the output. However, in real amplifier, there is always some variation or some error, and the ratio of the change to the output voltage with regard to the change of the common mode input is called common mode rejection ratio. So the smaller common mode rejection ratio the amplifier has, the better the operational amplifier will be. Now, this is the baud plot of the 741 op-amp. This is the frequency response of the 741. As you can see, guys, up to 10 hertz, we have the maximum gain of the op-amp, which is 100 decibel. Okay, this gain will decline by 20 decibel roll off until it reach the unity frequency at 1 megahertz. At unity frequency, the input will equal the output, so the gain will equal 1. We call it unity frequency. When the gain equal 1, we call this unity frequency. So it means that the 741 is suitable for frequency from 1 megahertz and less. Okay, 1 megahertz and less, this operation amplifier 741 is suitable for amplification. Okay, otherwise, if the frequency is higher than 1 megahertz, then you need to think of another operation amplifier. We have the 325 that has, I think it's 100 megahertz. Okay, but it's more expensive. So if your application has frequency less than 1 megahertz, then 741 is the right choice. Why 741? Why is it very popular? Because it's actually a cheap operational amplifier. Okay, that's something that need to consider. Remember the variation we said on the output? This is one of the practical way to pin out and offset nailing. We call it pin out and offset nailing. So we can adjust the output. We call it adjust for nail by using, this is the real 741. So pin 5 and 1 are used for offset nailing. All we need to do is connect a variable potentiometer between these two inputs, and we take a negative voltage, and we can adjust this resistor. Okay, so how do we do the offset nailing? We connect the non-inverting input and the inverting input to ground, That means this we'll have here 0 volt and 0 volt on this input. So the output should be 0. Now we bring a voltmeter and we measure the voltage on the output. If it's not 0 volt, then what we do, we will adjust the potentiometer until we can read 0 volt on the voltmeter on the output. Okay, we call this pinch and offset nilling. Okay, there is something that worth mentioning in this slide. We call it the slew rate. Okay, the compensation capacitor inside the 741 performs a very important function. It prevents oscillation that would interfere with the desired signal, but there is a disadvantage. The internal frequency compensation capacitor found in most op-amp also limit the rate at which the output can change. So the meaning here that in the circuit diagram of the op-amp, it's complicated. It has a dozen of transistors and resistors, and we also have a capacitor. The capacitor in the design is very important because it will remove the oscillation that would interfere with the desired signal. Okay, so it remove noises, but there is a disadvantage also from this capacitor. Also, it's very important to be there, but the disadvantage is the charging time and the discharging time of this capacitor. We call this the slew rate because if the signal is faster than the charging time and discharging time, we will have something effect called the slew rate distortion. And it's showing here, for example, this is a signal that has a high frequency. The frequency of this signal is faster than the charge and discharge time of the oscillator of the capacitor, sorry, the compensation capacitor. And as a result, we will have this signal instead of the, so there will be a distortion in the signal because of the slew rate. And the slew rate can be calculated with this equation. Okay, so the slew rate of the 741 is 0.5 volt for every 1 microsecond. Okay, so when the signal exceeds the slew rate of an op-amp, the output become distorted and amplitude limit. So as you see, this is the real signal, the red colored signal, and this is the signal with the slew rate. Why this happens? As okay, because the signal exceeded the slew rate of an op-amp. The slew rate of any op-amp will be seen from the datasheet. For the 741, it's 0.5 volt for every microsecond. The inverting amplifier, one of the most common application for the op-amp is to be used as an amplifier. And one of the most popular amplifier available is the inverting amplifier. In the inverting amplifier, we have a closed loop gain. As you can see, the output of the op-amp is feeding back through R2 the input, the inverting input. Okay, and the non-inverting input is connected to ground, and we have R1, the input resistor, and this is the source of the signal. So the output will equal the input plus the gain, the negative feedback gain. Okay, so to analyze this circuit, we assume a virtual ground here. Okay, this is not a real ground, guys. This is a virtual ground. The ground is short for voltage, but it's an open for current. So that's why we call it a virtual ground. Why we have a short for voltage but open for current? Okay, remember that the input, these two inputs has a very high input impedance. So basically the current is going through R2. Okay, R2, the resistance here is much less than the resistance of the input of the amplifier. So the current will pass. The voltage is always going to be 0 at this point because of the virtual ground. Okay. This will help us a lot in the or make the analysis of the inverting amplifier much. So when we do the analysis, we assume a virtual ground here. So the input current is going through R2, okay, and to the output. So the input voltage based on Ohm law equal IN times R1. So the input current plus the input resistance R1. And the output voltage can be calculated also from this resistor, the voltage on this resistor, which is IN times R2. As we said, IN is the same current going through both resistor. So again, IN times R2 using Ohm's law. Okay. So by this way, we can easily calculate the gain. Remember, the gain equal the output over the input. So V out over Vn, which equals R2 over R1, right? IN R2 over IN R1, and IN will go. So we have R2 over R1. The closed loop input impedance is equal R1. Okay. So as you can see, the negative feedback increases the closed loop bandwidth. So the closed loop bandwidth will increase by using a negative feedback in the operation amplifier. That's why we always tend to use negative feedback with the operational amplifier. You will see even in the next application, we also use a negative feedback because it will make the operation amplifier much more stable. So the frequency of the closed loop equal the unity frequency over the closed loop gain. You see the input and the output. So the output here in the inverting amplifier is amplified and it's inverted. The positive here will become negative and the negative will become positive. That's why we call it an inverting amplifier. Okay, so if the input voltage is negative, the output will be amplified and positive. If the input is positive, the output will be negative. Okay. While in the non-inverting amplifier, the signal will maintain its polarity on the output. So when it's positive on the output. When it's negative on the output. Of course, after amplification. Okay. The negative feedback, as you can see, we also have a negative feedback. It's not a positive feedback, a negative feedback. And we have R1 connected to ground, but the only different here that the input signal is going to the non-inverting input. Okay, so the input signal to the non-inverting input. You need to memorize the drawing of these applications. So how do we analyze the circuit? To make the analysis very simple, we assume a mental short of the input of the operational amplifier. Okay. So as a result, Vn will equal this voltage, because with this mental short, Vn and R1 are in parallel. So the voltage here equal the voltage of the input. So we can say that the input voltage equal I1 R1. Okay, and V out will equal the voltage on these two. V out is from this point to ground. So the voltage on R2 and the voltage of R1. So V out will equal I1 multiplied by R2 plus R1. Two resistors in series. So to find out the closed loop gain of the non-inverting amplifier, V out over Vn will equal R2 plus R1 over R1 equal R2 over R1 plus 1. Okay, so the closed loop gain for the non-inverting amplifier is R2 over R1 plus 1. Okay, while on the inverting amplifier it was R2 over R1. And the input impedance of the closed loop here is infinite. The third application we need to cover in this course is called the summing amplifier. And as you can see from the circuit diagram, the only difference between the summing amplifier and the inverting amplifier is that the summing amplifier has two input V1 and V2. Okay, so if you remove R2 from this circuit diagram, you will have the inverting amplifier. Okay, so we can have 2, 3, or 4, 5, and so on by adding more paths and a resistor, and then we can have V3, okay, and V4 and V5 and so on. So how do we calculate the output for this signal? As you can see, we are assuming the same closed loop gain of the inverting amplifier. So RF over R1 will be the gain for V1, and RF over R2 will be the gain for the signal V2. The output will be the sum of these two signals. Okay, so to calculate V out, RF over R1 times V1 plus RF over R2 times V2, and if we have a third input, it's going to be plus RF over R3 V3, okay, and so on. So a very simple circuit that do the job. Basically this circuit, if you have a unity gain, for example RF is 1 kilo and R1 1 kilo and 1 kilo, then this will be a summer only, okay, because the amplification will be the unity amplification 1. So this circuit, basically the output will be V1 plus V2. Okay, if you have the same value for the 3 resistor, V out will equal V1 plus V2. The last application we will cover in this course with the op-amp is called the voltage follower. The voltage follower, the input AC source has a high output impedance, R high, this one. The load has a low impedance, R low, okay. And as you can see, the negative feedback here is a direct feedback. No resistor is used here. So that's the highest feedback possible. Because of the maximum negative feedback in the voltage follower, the closed loop input impedance is incredibly high, and the closed loop output impedance is incredibly low. So we have a very high input impedance and a very low output impedance. So as a result, all the input source voltage appears across the load resistor. All the input source voltage appear across the load resistor. Okay, so the input impedance here will equal the output impedance. The benefit here, we have a high impedance source that can feed a low impedance output. So this circuit is very useful when connecting high impedance source or circuit with a low impedance circuit. It will be like a buffer to protect the low impedance circuit or load. Okay, so the closed loop gain for this amplifier is 1, no amplification. The input voltage equal the output voltage. The input impedance, closed loop impedance, is extremely high, infinite. And the ideal, if it's an ideal voltage follower, the output impedance is 0. And the the closed loop frequency equal the unity frequency. Okay. Some other type, we mainly focus on the 741 operational amplifier. It's, as I said, the most popular, the most common operational amplifier. Although there are some other type of amplifier, like the BI FIT operational amplifier, offer extremely low input current and a high power op amp supply amperes of output current. Okay. Also, this BFET BiFET operational amplifier has a high speed op amp slew. So that means it can exceed the 741 and go beyond 1 megahertz. And usually, as I said, some operational amplifier, the unity frequency is 100 megahertz. The precision op amp boosts small offset error and low temperature drift. So that's a better operational amplifier. But why we don't use this operational amplifier a lot, we mainly use 741. The main reason is this one is very easy to use, and the second reason is the price. This one is very cheap. You can I used to buy 741 with 5 real, and if you want to buy a BiFET operation amplifier, it might cost you 25 to 30 real. So that's a huge cut in cost, especially if you are making a project. One of the important factor that you need to consider in a project is the price. Okay, let's go through some example on this session. Remember, we only going to have 2 examples, and I recommend that you go through the other examples in the textbooks, chapter 18. So example 1, draw an inverting amplifier with a closed loop gain equal 10. So basically you need to draw the inverting amplifier. So let's draw this inverting amplifier. So we have a triangle, and we have the non-inverting input and the inverting input. In the inverting amplifier, the non-inverting input is connected to ground. You can put a resistor or without. And we have the inverting input. We have a resistor, input resistor, and we have Vn. Okay. And we have a single output, Vout, and we have a negative feedback resistor. We will call this one RF, and this one we'll call it I or I1. And that's the inverting amplifier. So the only remaining now is what's the value of Ri and Rf to give us a closed loop gain equal 10. So the closed loop gain required is 10. Okay. And for the inverting amplifier, as we saw in the analysis, ECL equal minus RF over Ri. So that's the closed loop gain for the inverting amplifier. Okay. So how we can determine the value of RF and Ri to give us 10? Most of you will directly say 10 over 1 will give us 10. But let's take this step by step. So the first step you need to do here is to by assuming RF, we can assume RF, or we can assume Ri. We'll assume RF here to be equal 10 kilo ohm. Sorry. So RF equal 10 kilo ohm. So let's find Ri then. So Ri will equal RF over ACL. So that is 10,000 over 10. So we will have Ri will equal 1 kilo ohm. 1 kilo ohm. So go back to the circuit. So I will have this 10K and here 1K. So that will be the answer to the question. Okay, the second example. We have 3 audio signals drive a summing amplifier, as we can see in the figure below. What is the output voltage? So we have a 3 summing amplifier with 3 input. We have 3 different resistors at the input. We have 10 kilo for the V1, and we have 20k for V2 and 30k for V3, while the feedback resistor is 100 kilo ohm. So how we can find V out? Now we know that V out will equal the gain of the first input, which is minus RF over R1 multiplied by V1 plus minus RF over R2 multiplied by V2 plus minus RF over R3 multiplied by V3. Okay, so that's mean we have minus 10, right? That's 100 kilo over 10 kilo is 10, so minus 10, and V1 is 100 millivolt. Remember, this is V1 here. Okay, plus minus 5, which is 100k over R2, 20k, and V2 is 200 millivolt plus the gain for the third input, which is minus 2.5 multiplied by the 300 millivolt V3. Okay, so that will give us minus 1 plus minus 1 plus minus 0.75, which is minus 2.75 volt. So that will be our output voltage, minus 2.75 volt. Thank you.